Okay, welcome everyone to the second talk of this morning. Our speaker is Sergiy Merenkov, and he will talk about symmetries of Julia sets. Please.
Thank you, David. I would like to thank the organizers for inviting me, Artyom, David, also Piotr and Felix. Thank you. It's a pleasure to be here. That's my first time in Poland. I'm enjoying it so far. I also would like to thank Poland and Polish people for providing so much support to people of Ukraine who are in need. Thank you. So I will talk about symmetries of Julia sets, and rather quasi-symmetries. And this talk is based on several Julian projects with subsets of these people. Mario Bonk, Russell Lodge, Misha Lyubich, Sabya Mukherjee, and Dimitrios Ntalampekos. Some of them will be giving talks later in the conference. Okay. So, yeah, as I mentioned, I will talk about quasi-symmetries rather than symmetries of Julia sets. And quasi-symmetry, just to remind or maybe to tell if you don't know, so X and Y here are metric spaces, and the quasi-symmetry is a homeomorphism between metric spaces, which has the following property. There is a distortion, so-called distortion function, which is itself a homeomorphism of this half open, so this array from 0 to infinity to itself, such that for arbitrary 3 points O, P, and Q in the metric space X, you have this inequality. Okay, you have this inequality, which is a little too much to digest maybe at first glance, but geometrically it means the following. You take an arbitrary ball in a space X, centered here at P, radius R. You map it over with your homeomorphism, and generally you should expect some blob like this. Okay, and you should be able to inscribe a disk of some radius capital R1 and circumscribe a disk of capital R2 radius. And certainly you can always do this for any homeomorphism, but the main defining property is that the quotient here should be at most a constant, and this constant doesn't depend on either the center or the radius. Okay, so basically quasi-symmetric maps, they roughly preserve shapes. So something round goes to something roundish, not necessarily round, roundish, but the scales may change dramatically. Okay, so this is little r and these are capital R's. Okay, these are quasi-symmetric maps. And so since we are in Poland, I should probably start with a Sierpiński carpet Julia set. And so this particular example is a Julia set for this degree 4 map, z squared minus 1 over 16 z squared. This is also a post-critically finite rational map. And post-critically finite is what Julia defined already. You look at the set of critical points, you iterate them, you should end up with a finite set, not an infinite set. So in this particular example, the immediate basin of infinity is fixed, as you can see from the formula. The neighborhood, this is the origin, neighborhood of the origin here gets mapped. Maybe I'll draw gets mapped. Let's see here. Okay, and then this stays, and then some of this. So all of this, actually, all of this for two components, they eventually get mapped. I don't remember if this I drew this correctly, but eventually, you know, whatever you for two component you take, eventually it gets mapped here and then spits out. Yeah, and then fixed. Okay. So this is one example of a Julia set. I refer to it as a carpet Julia set because it is homeomorphic to the standard Sierpiński carpet, the standard one, which is like this, right? So they are homeomorphic to each other. Okay, so there is a large family of such Sierpiński carpet Julia sets. And what we would like to know in particular for this example is what is the group of quasisymmetries of such a Julia set. And by the way, quasisymmetries, they do form a group. So inverse of a quasisymmetric map is quasisymmetric itself. And so is the composition of the quasisymmetric maps. Okay, so we would like to describe a group of this. For example, such a carpet. See how large it is. And then based on how large it is, we will also try to classify carpets or not necessarily carpets. Later on, you will see some other Julia sets as rigid or non-rigid. Like if you only have a finite group, we will say it's rigid, otherwise flexible or non-rigid. Okay, and the first result I will mention, and this has been already a little while ago. This joint work with Mario Bonk, Misha Lyubich. We proved that for any post-critically finite rational map, for example, that one, whose Julia set is a carpet, is a Sierpiński carpet, so homeomorphic to the standard carpet. Every quasisymmetry would have to be a restriction of a Möbius transformation to the carpet. Okay, a restriction of a Möbius transformation. So, so a priori, yeah. For example, there are many, infinitely many homeomorphisms, self-homeomorphisms of a carpet. In particular, this carpet. In fact, you can prescribe. Like you can choose finitely many of this Fatou components, and you can prescribe where you want them to be mapped. Let's say here, here, and I don't know, here. And you can find such a homeomorphism that does it. But you cannot find necessarily quasisymmetric homeomorphism that does it. There will have to be restrictions of Möbius transformations. And one of the speakers today, we used a result of Gennady Levin, who proved that in this case, the group would have to be finite. Okay, so this is a finite group. So it's a very rigid object from the quasisymmetric viewpoint. It's a finite group, and here you can identify easily some symmetries of this. So basically what this theorem says that every quasisymmetry is a Möbius symmetry. There are some, clearly rotations by pi/2 are symmetries. There are some reflections as well that are symmetries. There is another somewhat hidden symmetry. There is a symmetry with respect to 1/z for z. So z goes to 1/4z Möbius transformation that keeps this Julia set invariant. So there are some symmetries, but not many, finitely many only. Okay, so that is the first result I wanted to mention. And there are a couple of corollaries to this result. One that I already said, that for post-critically finite, so this corollary, for post-critically finite, you only have finite quasisymmetry group. This is again, so by Gennady. Another corollary, and that was one of the motivating questions for this research, that if you have a post-critically finite rational map, and if you assume that the Julia set is a Sierpiński carpet, and if you take an arbitrary Euclidean group whose a limit set is a Sierpiński carpet, they cannot be quasi-symmetrically equivalent. So this is again a certain classification result. They cannot be quasi-symmetrically equivalent because J, so for this you have J has finite quasi-symmetry group, and the limit set has infinite, so this is limit set, has infinite quasi-symmetry group of self-maps because the group itself acts on it, and it's an infinite group. Okay, so there's a whole infinite group action on, and this picture was taken from Kurt McMullen's page. He has a gallery. Here, Phi1 M3. So this is a limit set of certain fundamental group of convex compact hyperbolic manifolds, ring manifold with totally geodesic boundary, whatever that, I'm not going to go into detail, whatever that means. There is this nice, beautiful limit set. Okay, so they cannot be quasi-symmetric to each other, even though they are topologically the same. So, well, and going a little bit back also, Mario Bonk and myself first studied this question for standard Sierpiński carpet S3, and one of the results we proved is that any quasi-symmetric map here has to be an isometry. Has to be an isometry. So again, some pi over 2 rotations and a couple of reflections like this, but nothing else. And for the same reason, so such we called it S3, or somebody else called it S3. So for the same reason as before, as for Julia sets, this cannot be quasi-symmetrically equivalent to the limit set, as in the previous slide, again, because here you only have finite group, and in the limit set you have infinite group of quasi-symmetries. And it also can be distinguished from the Julia set in the previous picture as well, so it cannot be quasi-symmetric to the Julia set, just because Julia set has this more symmetries than this one. This one doesn't have any hidden like reflections. Okay, maybe it's reflections, and the Julia set does. So otherwise, they have the same symmetries. Otherwise. Okay. So that is concerning Sierpiński carpets. And we were inspired by this rigidity results for Sierpiński carpets, and well, decided to look at some other Julia sets. And chronologically, the second one we looked at was tree-like Julia set. In this case, it's in this picture, it is a basilica Julia set, very simple z² - 1 dynamics. Here you have this Bayesian at infinity, which is of course fixed. It's a polynomial. You have a 2-cycle, right? 0 and -1, -1, 2-cycle, and so on. So everybody here in a bounded Fatou component eventually gets mapped into this 2-cycle. Again, very simple dynamics. I shouldn't probably be explaining this for this audience. We asked ourselves, Misha Lyubich and I asked ourselves, what is the quasi-symmetry group here in this case? And we maybe initially, at least I initially thought maybe it's also a rigid, just like in the carpet case, but it is not. It is not, and we quickly realized that There is a large group acting on this set. There's a so-called Thomson group T, acting on the set. I will explain what this Thomson group is and how it acts on the Julia set. It's an infinite group. It acts faithfully on the Julia set. And there's also an inversion. And I will state a result later that these two generate the full group of quasisymmetries. So at least they don't generate the full group of quasisymmetries, but their closure does, the closure of T and this inversion. Okay, so let us talk about, and maybe I should talk about this Thomson group T here. Let's go back. So Thomson group T is a group of orientation preserving piecewise linear homeomorphisms of the unit circle, piecewise linear homeomorphisms that preserve every homeomorphism from that group has to preserve dyadic points. Dyadics have to go to dyadics. Number one. Number two, so this is piecewise linear. It has finitely many breakpoints, right? Points where slope changes. Those breakpoints have to be dyadic as well. Okay, and finally, the slopes, those finitely many slopes, they have to be integer powers of 2, like 2, 4, root, and so forth. Integer, so not the root, sorry, 2, 4, 1/2, and so forth. Okay, integer powers of 2. And this is Thomson group T. There are two other Thomson groups which I will not mention, but from this definition, it's actually unclear, but it is a fact. This group is finitely generated. So there are only 3 generators for this group, and they're listed on the next slide. They're usually referred as A, B, and C, I think, in the literature. This is supposed to be, let's see if I can make it larger. Well, it's okay. So generator A, depicted here, this is interval from 0 to 1, but you should think that this 0 and 1 are identified, right? Because we're in a circle. 0 and 1 are identified. So this has 3 breakpoints, 1 at the origin, 1 at 1/2, and 1 at 3/4. This is 0.75 right here. The slopes are on 0 to 1, the slope is 1/2. Then the slope is 1 and followed by slope 2. Okay, this is one of the generators of the Thomson group T. 2 others are depicted here. This one has 4, 1, 2, 3, 4 breakpoints. A little hard to see, but there are 2 breakpoints here. And this one has 3 again. This one, so the A and B, they fix the origin. They have 1 fixed point here, the origin. And C actually doesn't fix the origin, which is not super clear from this picture, but this doesn't start, unlike these two, they start at 0. I hope you can see that this is 0 right here. This is 0, and this is 0.75. So it's not only, so it's also a shift. Okay, it's also a shift. It doesn't fix the origin. So these 3 elements, they generate the full Thomson group T. Okay. And now I should probably explain how they act on this Basilica Julia set. So F is z² - 1. As you can see, I only take even powers here, 2, -4, 2, because this group action T fixes this big Fatu component. And I need to go to the even power so that I actually come back. Okay. F2 fixes this Fatu component, and in the Böttcher domain, in the Böttcher coordinate, it's just z squared. It is just z squared, right? And z squared has, it's on the boundary circle. Z squared is angle doubling, right? So the slopes of any f to the n, 2n, f to 2n, where n is integer, will be integer powers of 2, right? Just as required by Thomson's group. And so A, that's the first generator on the previous slide here. Oops. A. Here's the action of A on the Julia set. So you first take f minus 2 for t between 0 and 1/2. So you're looking at this central component, a 2 component. T between 0 and 1/2 specifies this part here, this part. Okay. And you define the action of A on this part as f minus 2. So it takes this part to this quarter part. Okay. And you also, so f extends, right? And f in inverse f minus 2 also extends to, well, at least part of the plane. So actually all of these limbs that stick out from here, they would also be mapped accordingly, right? According to this formula f minus 2. So like, for example, this part will get mapped to this and so forth, right? So you take this, including all of these decorations, and you map them by the formula f minus 2. And that has the effect of slope 1/2 here on this part. Slope 1/2, right? So we're mimicking this A on the Julia set. And then on this part, we have f minus 4 f to the 4. So think of it as slope 1, right? Slope 1. And finally, on this part, it's slope 2, right? So, and we defined the action on the whole Julia set using this piecewise formula. Okay. And you can also define, similarly for B and C as well. For B and C, I didn't specify it here on the slide, but you can. And what is this inversion that I mentioned a couple of slides earlier? This inversion right here. The inversion. So this is a fixed point. This is a fixed point, and the inversion is f to the right of this fixed point. So I'll draw it. So f maps this part to interchanges this right and left parts. This is right, this is left. And f inverse maps here, or the other way around. So let's see. No, the other way around. So this is f, this is f, and this is f inverse, right? Yeah. Like this. Yes. Okay. So that's the inversion. And so group T fixes the central component, fixes this component. T leaves this fixed, but I interchanges these two. And you can see that successively applying these elements of T and I, you can actually take, it's a very simple exercise. You can take any bounded Fatou component and map it to the central Fatou component just by some rotations and flipping. Okay, you can bring it to the central Fatou component. And in fact, you can also, once you convince yourself of that, you can also see that if you have any finite subtree, so you take finitely many Fatou component, bounded Fatou components that are connected into a tree, and you have any other such a tree with the same combinatorics, you can map one of them into another by applying those elements. Okay, applying elements of T and the inversion. You can do this.
Excuse me, just a quick question. So when you take a closure, you get uncountable group, right?
Yes, you get uncountable group. Yeah, I didn't get to this part, so to this theorem, but yes. So let's see. Right. So that is the main result here for Basilica. With Misha Lyubich, we proved that if you look at this group, which we call T hat, generated by T and the inversion, then any quasisymmetry can be approximated by a sequence of quasisymmetries, approximated in the uniform sense, by a sequence of quasisymmetries. And the important subtle part here that you can make them uniform. So this eta prime is the same for all n, the same for all n. For all n. Same for, so for any eta distortion function, you start with an eta quasisymmetric C. And then there is a distortion function eta prime, maybe different, so that C can be approximated by a sequence of Cn with the same distortion. So that procedure that I described, I mean, it's clear that you can approximate in this way, but there is no control on distortion, right? You cannot say anything. But in fact, you can control distortion as well. This group, T, which we call T hat, so we learned, after we completed the work, that the algebraic properties of this group were considered by Belk and Forrest in an earlier paper, but they didn't study this quasisymmetric aspects of it. And they also, the description of the group was a bit different. So they looked at the Basilica lamination, and they looked at all the piecewise linear homeomorphism of the circle that preserved that lamination. Okay. It turns out that this group, if you think of it in terms of laminations, is the same as this group generated by a regular Thomson group, as well as the inversion, same groups. Okay. So that's the result. And as you can see, this is right. So as Artyom mentioned, you would get, the closure would give you uncountable group. So this is a very flexible object quasisymmetrically. You have many quasisymmetries acting on it. Okay, so when we did complete this, we thought a little bit about other similar Julia sets, for example, rabbit. And you can also describe, I mean, using the same tools, you can describe the group of quasisymmetries for the rabbit, for example, or for any Julia set of a quadratic polynomial that you can obtain by finitely many bifurcation from the main molecule. Okay, so what Julia also mentioned. He had zero entropy on that set, so that's this one falls into that category as well. So you can handle this one as well. The group will be, I mean, except for the inversion and Thomson, some kind of Thomson group, you would also need add some rotation elements and whatnot, but you can certainly handle it. What you cannot handle using our techniques is some other Julia sets, like airplane Julia set, where you don't have this. I mean, you do have a tree structure, but the bounded for two components are not attached in a tree-like structure. So we cannot do that, but could not do this. But a student of Misha, I think, worked on this and has some description for a group like that as well. Tim. Okay, so we now move to the last topological type of Julia sets that we considered is the Gasket, Sierpiński Gasket Julia sets. And there is a subtlety here that I will talk more about. You can see that this is F bar, so this is complex conjugate. So we will talk about anti-rational maps here. Okay, so it's a complex conjugation of a rational map. You will see why this is natural to look at anti-rational rather than rational maps in this context. And a short answer is that we relate them to some reflection groups which change the orientation. So we'll need anti-rational rather than rational. This particular picture gives you degree 3, or since it's anti-rational, maybe a correct way to say -3 degree -3 map. Okay, and that's a picture of it, and you can recognize here. This is a part of it. So Apollonian gasket here, and so forth. Right. So same question that we wanted to address is what is a quasi-symmetry group of this, whether it's rigid or flexible, and so forth. And we didn't just want to restrict our attention to just one particular one, to this one. We wanted to encompass the whole class of such rational maps, whose Julia sets have this gasket-like structure. Okay, and gaskets by no means are topologically unique. So there are many different gasket-like Julia sets, unlike carpets. And the class that, and this is work with, so I'll start with this work with Russell, Lodge, Misha Lyubich, and Sabya Mukherjee. We constructed this class using circle packings that were well popularized by Thurston. So what do you do here? You start with arbitrary triangulation of a circle. Arbitrary triangulation. I picked this sort of the simplest possible triangulation, almost the tetrahedral triangulation of the sphere. I don't know if I said the circle of the sphere. So you take tetrahedral triangulation of a sphere or any other triangulation of a sphere. Thurston Andreev Kerber theorem says that there is a circle packing that corresponds to such a triangulation. And the circle packing is a collection of disjoint disks in the sphere. So the disks correspond to vertices, and two disks are tangent, externally tangent, if and only if the vertices are connected by an edge. Okay, and there's a Thurston Andreev Kerber theorem says that you can always do this for an arbitrary triangulation. For the tetrahedral one, it's this. So the circles are in black here. So there are 4 circles corresponding to 4 vertices, and they're pairwise tangent, like you expect. What we would like to do, given such a circle packing or a more general circle packing, we would like to produce anti-rational map for which these circles of the circle packing become fixed for 2 components. Okay, fixed for 2 components. And so the way we do it, because we want the circles to be fixed for 2 components, we have to look at the dual circle packing. And because we start with a triangulation, there is a well-defined dual circle packing, right? Triangulation tells, since it's a triangulation, it tells me that there are this kind of triangular interstices, and you take 3 points of such a triangular interstice, you take a circle through those 3 points. Right? So the yellow or red, rather, red are parts of circles of the dual circle packing. Okay. So we look at this, and if you look at the group of reflections with respect to this red circles, it's not Kleinian, but it has index to Kleinian subgroup. Kleinian would have to be orientation preserving. So these are reflections. They're not, but so almost Kleinian. And the limit set is what you would expect is this Apollonian gasket in this particular triangulation. But if you look at some other triangulations, you will still have gasket-like structure. Right? Now, I mean, it was not our business to talk about, to discuss quasisymmetries of limit sets, we wanted to have Julia sets. And first, to construct a Julia set out of a circle packing like this, the first step was to create or to produce branch covering of the sphere. Branch covering of the sphere. And here how it works for this particular circle, very simple circle packing. So you look at this triangular interstices, this one, so there are 4 here. And on each one of them, you define your branch covering to be reflection here. And reflection, I called it N because there's this Nielsen's map defined on this triangular interstices. And Nielsen's map is a piecewise defined map on those triangular interstices that's reflection on each respective interstice. Okay, we call it Nielsen map. This is Nielsen's map. Okay, so it's defined here, here as a reflection in the corresponding red circle. Yeah, so in this triangular interstice, it's a reflection in this circle and so forth. And then the map is everywhere defined except on the actual original disks of the circle packing, right? It's not defined on the disks of the circle packing on these white disks. And we define it using this z bar d minus 1 map. So what is d here? D is the number of triangular interstices on the corresponding disk. Oops. On the corresponding disk. So in this case, d equals 3. Okay. So on this disk, we define it essentially as z bar squared. And unlike z squared, so z bar squared has 3 fixed points on the circle. So z squared has 1, so z bar squared has 3. Okay, it's a simple exercise. So you have the 3 fixed points, right? And I mean, we just think of them as roots of unity, cube roots of unity, and define it as z bar squared on this one, on this one, on this one, and on the exterior one. Okay. And so we have a branch covering, but it's orientation reversing branch covering of the sphere, and you can also count the degree of this branch covering. Degree will be number of this triangular interstices minus 1. So in this case, degree will be 3. You can easily count that. And once you have a branch covering, whether it's orientation preserving or not, the first thing to do is to see whether it has some Thurston obstructions or not. But again, Thurston obstruction is for orientation preserving, so we had to modify this business a little bit to work for orientation reversing maps, and we could. And it turns out that whatever triangulation you start with, it would not have any Thurston obstructions. It would not have any Thurston obstructions. Because it doesn't, and this followed from results. So we used the result of Kevin Pilgrim and Penley to check that it has no Thurston obstructions. And so we have anti-rational map of degree 3 in this case. And that's exactly that picture that I started with. So for this particular tetrahedral packing, circle packing, that's the corresponding map. Anti-rational map of degree 3. Okay. So now, right, going back, we would like to describe the group of quasisymmetries of this. And we needed some technical definition to describe. I mean, we could do it for general triangulations, but it's the nicest for so-called reduced triangulations of the sphere. So reduced meaning that if you take any triangle in your triangulation, it would have to be boundary of a face. And this one is not reduced. So if you take double tetrahedra, if you take 2 tetrahedra and combine them like this, like in my picture, This is not reduced. So it has triangle that is not, so like this triangle is not the boundary of any face. So this is non-reduced. Okay. So we actually wanted to have reduced ones. And as far as this reflection groups and limit sets are concerned, this is the difference is very minor between reduced and non-reduced. So like if you have here, if you have tetrahedral circle packing and you double across one of the circles, right? This is reduced, this is non-reduced. I'm doing something that not sure. This is not reduced. And you see, so all that happened is just I reflected my original circle packing with respect to some circle and got non-reduced. And this is a very kind of benign operation, right? Basically what I did is I took a index 2 subgroup here. And the limit sets of this guy and this guy will be exactly the same. Exactly the same, right? The limit sets for the two groups. But it turns out that for the Julia sets, they will not be exactly the same. So the corresponding, we have a picture that one that you've seen before. This is a tetrahedral Julia set, and this is Julia set obtained from this other non-reduced triangulation for the double tetrahedron Julia set. And topologically, they are the same. They are exactly the same, but not geometrically. I mean, you can see that there are more kind of the bigger angles here, more pronounced angles than this. So, and also, it's a little hard to see. That's supposed to be, I mean, complex conjugation of the whole thing. This is a degree 5 map. This is, well, or -5 rather. And it's also an orientation reverse, and this is -5 degree, and this is degree -3. So, and one interesting consequence of this, even though reflecting with respect to this one circle, we just get a subgroup of index 2, right? These two anti-rational maps, so like this anti-rational map is not an iterate of this one. It cannot be, because this has degree -3, this guy has degree -5, so that's not an iterate. As far as Julia sets are concerned, the relationship is more subtle than just like taking finite index subgroup when you reflect. Okay, and here's the main result for quasisymmetries of this Gasket Julia sets. So we took, this is a tetrahedral one, but slightly different picture. So it's in the plane. The quasisymmetry group of this Julia set is the same as a group of homeomorphisms. So this is what one can call like topological rigidity in some sense. So they're unlike carpets where the two groups are vastly different. The group of homeomorphism is huge, group of quasisymmetries is finite. These two are the same groups. They also, because the Julia set and the limit set are homeomorphic to each other, these groups are isomorphic. Okay, Julia and the limit set. And for the limit set, you can also describe the group. This is a semi-direct product of the group G. This is the group of reflections in the limit set lambda in the dual circles. G is the group of reflections, and this is a finite group that preserves this triangulation, that given tetrahedral triangulation. Finite group of, these are Möbius transformations that preserve this picture, this triangulation here. Okay, so I mean, there's this inner automorphism group and outer automorphism group, whatever that means, but this semi-direct product here. So we can describe it, and the quasisymmetries are defined in this piecewise manner, just like those inversions that I discussed for basilica. for any delta here is a triangular interstice. So for any triangular interstice, you can produce a quasi-symmetry in this group, which is F on the triangular interstice and F inverse on the complement of such a triangular interstice. So you can like really describe the maps. And these are all of them. Okay. There are also infinitely many, but the topological and quasi-symmetric groups are the same in this case.
They're countable.
Yeah, so yes, here you will have countable group, yes. Okay. So, I mean, the last 5 minutes or so that I have is we and Sabya and maybe Dimitrios also, I'm not sure, we'll talk more about this part in their respective talks. Sabya for sure. So we know that this is homeomorphic to the limit set. That's a Julia set, tetrahedral Julia set. That's a limit set here. We know that they're homeomorphic, but clearly they cannot be there is no quasi-symmetric map from this one and to this one. There's no quasi-symmetry. They have the same quasi-symmetry groups, right? So we cannot distinguish them by just looking at their quasi-symmetry groups. We cannot. They have the same ones, but there is no quasi-symmetric map between them. And you can see this because this have non-zero angles and this has zero angles, and quasi-symmetry in this case would extend to quasi-conformal homeomorphism of the sphere. So they're not quasi-symmetric, but it turns out that there is a David relation between them. That's sort of the next best thing that can happen. And because I'm running out of time, so there is this class of David maps. These are locally in the Sobolev space 1, 1. Their Beltrami coefficient can degenerate. It can get close to 1, but in some exponentially controlled way. Okay, and there are a couple of equivalent definitions for this. And again, I think Sabya is going to discuss this in more detail. In particular, it's exponentially integrable distortion, dilatation, exponentially integral dilatation. And so basically, yeah, let's go back and look at this picture. So there is this there's a hyperbolic dynamics on this one, on this picture. F, it's a hyperbolic map, orientation reversion, but still. And there's a parabolic dynamics here. There are some parabolic fixed points, right? And we would like to relate this to. And I mean here, right, if you uniformize this, so, one of these fixed for two components, like this one, or this one, or you will see that the map in the unit disk is z bar squared. Okay, here you're not going to have hyperbolic dynamics, but if you basically go from circle to real line, so between 0 and 1, you will see this pattern of circles, right, in your limit set. This pattern of circles, and they're called Ford circles. And the sequences where they touch the real line are called Ferry sequences. And you might be familiar with this. And so if we are trying to relate these two guys by David map or some other map, you would have to match the angle doubling, right? Angle doubling map on a boundary of such a photo component to this to map that takes these circles to circles, which is not angle doubling at all. And this is, I really like this picture a lot, and this so it's amazing that how these circles are aligned. For example, if you want to know where this circle in the middle touches the real line, what you have to do is you would have to add these two fractions, but in not as fractions, but you add numerators and denominators separately, right? So like this. So it's like, I don't know, I really like this. And the radii is actually 1/2 to the denominator squared. So there are some beautiful algebraic properties of this, and the distance between these 2 points is 1 over the product of the denominators and so on. So you would need to relate kind of homeomorphism, double angling homeomorphism from 0 to 1 to this homeomorphism. And you can, but your homeomorphism H would not be, so it would not have kind of quasi-symmetric property, but it will have this n depending on the level 1 over 2 to the n. So if you take 1 over 2 to the n level, this quotient will be bounded by something times n and 1 over constant n, right? So you don't have quasi-symmetry. This is not a quasi-symmetric, cannot be quasi-symmetric map, but this is a map like this. And the result by Chen here and also Zakiri show that if you define a scale-wise distortion, which behaves like log 1 over t, and this does, then it has David extension. Okay. And I will just, so I'm out of time, I will just finish with a couple of pictures that a couple of results that we discussed. So you can have a global David conjugacy between this anti-hyperbolic polynomial dynamics and the circle packing dynamics. You have a global David conjugacy that does it. And here's another picture that's just polynomial picture. And we also discussed, and again, maybe Sabya will talk more about this, the mating of polynomial and reflection groups. So this is a mating of triangular reflection group you see inside of this blue. This is you can see some images of triangles and the cauliflower map on the outside. And also we were able to produce such mating using David business. And that's the last picture I have. This David, so this maps here, reflection maps, are not defined on the whole sphere. So in this particular picture, your map is not defined on this triangular interstices because Nielsen map is not defined on the whole sphere. So we needed a different realizations here, not like Thurston's realization. And the proper setup here is this, which Sabya will discuss, is this Schwarz reflection maps. And in this picture, the Schwarz reflection map is defined on this deltoid and the circle. So it's defined outside of the deltoid and inside of the circle, but not defined on this. Okay. And this picture also the common boundary of the blue and red, green, blue, and the yellow is also a Sierpiński gasket as well. Okay, I will stop here. Thank you.
Thank you very much. Are there any questions for Sergiy?
So you stated that for Sierpiński carpet, like when the Faddeev components are very separated, you have a finite group of quasi-symmetries. And for like some cases like Basilica or Rabbit, when the Faddeev components are like very touching, you have infinite group of quasi-symmetries. But do you know, like in between of these two cases, like if you take just some arbitrary Julia set, can we say something whether they like it's rigid or not?
Yeah, so it seems like, I mean, from our experience, you really need to look at case-by-case basis, really. There's all of these techniques for carpets, for gaskets, and for tree-like sets, they're all very different, very different. I mean, there are some overlaps, like we used conformal elevators a couple of times, but very different tools. So we don't have one unified series. So like if you would give me a Julia set, some other we didn't consider, I probably would not know the answer, what kind of group it supports as a quasi-symmetry group. So unfortunately not. We have examples of finite groups, infinite countable, infinite uncountable, but no clear, like nice classification in general.
But for example, for airplane,
Mhm.
Is it infinite?
Yeah,
or-
it would be infinite. Yes. So you can also see there is a Thompson group acts on this central component, but it's more than that. It's not enough to just look at some involution and Thompson. You have to do something else. It has more structure. Like if you intersect it with a real line, you have Cantor set worth of points. So you have to account for that set as well. It's more subtle. Yeah, and the team, Misha's student was working on this. I'm not entirely sure about the status. I don't know if he did it or not.
Thank you.
Any other questions? No.
Maybe a naive question. Should one expect that every David symmetry of a carpet is Möbius? So speaking about the difference between quasi-conformal maps and David maps.
So let me think about this. I think so. Yes, I think so. You just, I think it's just enough to have some sort of Sobolev regularity. Really, you just need. We use this kind of a version of transboundary modulus of Schramm,
Right.
and invariance of this modulus for such maps. And really, all you need is absolute continuity kind of property. So I think the answer to your question is yes.
So it applies to much
Yeah.
bigger class.
Yeah, it applies to bigger class. Yeah.
Okay.
Any final questions? Perhaps online? If so, unmute yourself and ask directly, please. Okay, if not, then let's thank Sergiy again for this nice talk.
Thank you.
We have a coffee break now towards the reception.
Please sign up for the kayaks if you could do it during the break. This is very. Yes, yes, of course. No, it's not.